Hello everybody, and welcome to this video lecture on operations research. And we are in chapter 7 now on the lecture notes linear programming with SPICE, and page 21 at this point. So maybe I'll just before going on point out that yes, these notes are still under preparation. So these are revised at September 29th, and chapters 5 to 8 are finished at this point. So we are in chapter 7, and we are looking at reduced costs, also known as opportunity costs. So what are these? So as in the introduction in this, for this chapter 7, we said that these are related to this objective function of an LP, so objective parameter C, and in some sense the other sensitivity parameters that we just considered, the shadow prices, are, you could say that they are more or less only related to this optimal value. The reduced costs, also known as opportunity costs, are somehow more closely related also to this X star, that would be the optimal decision, and again depending on parameters C, A and B. And now we are looking at the parameter C, what happens when it changes. And unlike in the as in the case of the shadow prices, where the shadow price is related to this B, where just the partial derivatives of the Z star with respect to this B vector or its components, the reduced costs are actually not partial derivatives, so the interpretation is slightly complicated. I'm sorry about this. I really tried to find out myself, and even googling some and looking some other operations research notes, whether there is a simple or a compact definition for this, and it appears that there is not. So this is the easiest one, I think, easiest definition for the reduced cost. So here is the definition. The reduced cost UI, so U is a typical notation for it. So the shadow prices were lambdas, and okay, these are U's. So UI is a reduced cost associated with the coefficient CI. And now there are kind of two important cases. So if the xi star, meaning that value of the decision variable x, I star at the optimum, so this xi star is the component of this x star, if it's not zero, meaning, for example, if there's a product selection problem, then the reduced cost associated with it is zero. Okay, so the reduced costs are only interesting really when this xi star equals zero, and then now comes the interpretation. So UI is the amount CI has to improve to make xi star non-zero. So what do we mean by improve? Well, if this is a minimization problem, so now I'm talking about the minimization problems for a short while, usually I assume maximization. So if this LP is a minimization, then the CI, that's probably the name why it's called C, is the cost of doing xi amounts of these decisions. And if it's zero, this xi star, it means that it costs too much. We are not going to do it, so we have to reduce the cost. And then how much do we have to reduce the cost? Well, that's the reduced cost hence the name UI. Okay, so much for the minimization. Let's go to the maximization, which I prefer for some aesthetic reasons. So in that case, it says that, for example, if we are producing cakes and it was the Harkonnen cake X3 that was 0 in the more deep problem, 4.1 and 5.1, that was the problem, then it means that we are not getting enough of Solaris out of it. So they are too cheap. So the CI is not big enough. So it means that we have to increase it. And the question is, how much do we have to increase the price of Harkonnen cake at this point to make it profitable for us to bake them? So make this XI star, or X3 star in this case, non-zero. And again, the same thing. The amount is the reduced cost associated with this variable. Okay, so relatively strange concept, I suppose, not so straightforward as a partial derivative. The reason for this concept, I think, is that we will later learn when we solve, look under the hood of GLPK and talk about so-called simplex algorithm that actually solves these LPs, that when we solve an LP, we will automatically receive these reduced costs. So it's no extra effort to calculate them. When we solve the LP, we will get them automatically. And we will get automatically, of course, also the shadow prices. So I suppose that's the reason why we are interested in them. Okay, but then let's see what we can do with it. So this is the problem 7.10. This is the, again, I would say the key problem for us to understand what the reduced costs are all about. So if you understand what's going on here, then I expect that you understand what are reduced costs, and if not, then maybe not. So let us consider essential problem 7.10. I call this the Bene-Gesserit conscript training. And now, if you remember the problem 7.1, so this was Muad'Dib's jihad. So now it's not Muad'Dib, it's not baking anything. He's building a rapid deployment force. So he's no longer a baker, but a new emperor now. And the idea was, well, let's look at the problem 7.1, just to recall what was there. So this was the problem 7.1. So Muad'Dib, new emperor Paul Muad'Dib, has overthrown the previous regime, and now he has new dynasty, and of course new dynasty has to somehow solidify his power, and for that he decided to build a rapid deployment force with three kind of forces: Fedaykin, conscript, and Atreides conscript, and Sardaukar. And then there were some constraints about the resentments of different planets, what kind of forces there can be sent, and this was a maximization problem. So the pacifying influence of this rapid deployment force would be something, is this Z, so there is 10 units per each Fedaykin legion, 1 unit per each conscript, Atreides conscript legion, and 7 units for each Sardaukar deserter legion. Okay, so this problem was modeled and solved, and now we look at a bit more closely from the reduced cost point of view. So what happened in the solution was like this. So now I put here stars to denote that this is actually the optimal solution. In some version of the notes the stars were missing. of course that's not wrong, but it's better to have them here to really emphasize that we are looking at an optimal solution. And in the optimal solution, what happened? We have 370 leads on Fedaikin zealots, no Atreides conscripts at all, and 225 legions of Sardaukar deserters. So that was the solution 7.4. You can, and maybe at this point you should go back there in the notes and look at how the solution was calculated, or to be more precise, how we told Octave's GLPK function to calculate it. Okay, but of course the 0 here points somehow stands out. So there will be no Atreides conscripts at all in this rapid deployment force. Okay, maybe this is fine, maybe we don't want to have them. But then, of course, it begs the question, why does this happen? And one obvious reason for this is, or one way of looking at this, is that they are not influential enough. So remember, Fedaikin had an influence 10, conscripts had influence 1, and the Sardaukar had influence 7. So obviously they had very little influence of these conscripts, so maybe we can improve their influence, and then it could be useful to have them. And indeed, now the case is that the Bene Gesserit, they have promised to teach Atreides conscript the so-called Weirding Way fighting technique. So this is a special Bene Gesserit fighting technique. And I mean, this technique should make the Atreides conscripts more influential, better soldiers, more influence, and so on. And yes, in a situation like this, of course, there is no such thing as a free lunch, typically. So the Bene Gesserit will demand a price for their service. Okay, let's not go to the price whatever it is. Let's say that there is a price to pay. And the question is not how much to pay. The question is how much should the Weirding Way increase the Atreides conscripts' influence before any negotiations of the price with the Bene Gesserit make any sense. I mean, if it will increase the influence, say a little bit, but not enough so that it would still make no sense to have these Atreides conscripts in the rapid deployment force, we wouldn't even start to negotiate. So the question is, how good should this Weirding Way fighting technique be in order for us to make this X star 2 non-zero, so that now the Atreides conscripts are influential enough so that we will have them in the rapid deployment force. So this is the question. And yes, this should be somehow related to the reduced cost. And what is the somehow, before going to the reduced cost as such, let us look, can we somehow calculate this or understand this without this reduced cost concept? And well, yes, of course. And here this is the remark 7.11, Bene Gesserit training reduced cost. So let us start without the concept of reduced cost. So let us have this Z star, the optimal solution of the Muad'Dib Jihad problem. So these are the x's related to it, and then this Z is the influence related to this optimal solution. So Z star is the C times X star, C transpose times X star, of course. Okay. So let us then use a little bit of vector notation. This might be a bit uncomfortable for you if you haven't had a lot of experience, for example, in multivariate analysis, but it's good to get used to these, especially since vectors and matrices are what we use in Octave, and it's actually a very efficient way to write things shortly and precisely. Okay, so what happens here? If we make a deal with the Bene Gesserit and they teach the weirding way for the Atreides conscripts, then what changes is that we have a new optimal influence, Z star, where this A and B are the same. So A's were the resentments of the planets related to the different troops. B's were the tolerance of resentment in these planets. We assume that they are unchanged. Whether this is realistic or not, that's a good question. And then the new vector C plus delta 2 E2. So this would be the new influences of the legions of different troops when the weirding way is delta 2 effective, meaning that the Atreides conscripts index 2, that's why there is E2 and delta 2 here. So this here means that C2 is increased by delta 2. Okay, this looks maybe a bit complicated. Let me show you quickly on Octave what does that actually mean. So in this case we had C equals, let me remember if this is correct, 10 was for the Fedaykin, 1 for the Atreides conscripts, and 7 for the Sardaukar deserters. Okay, so E2 will be a vector with the second component 1 and otherwise zeros. So this is the unit vector of the second dimension. Alright, x2 dimension. And let's have delta 2, just for the sake of example, say that it will increase the influence by a half unit. Okay, so it's like this. So now we have C, E2 and delta 2 like this. So what is then C plus delta 2 times E2? So this here is what we have here. So you see, the first component here is untouched because we add something times 0 to it. The third one is untouched because we add something, so the something is delta 2 times 0 to it. But the second one, 1, is increased by a half because we multiply it by 1/2 times 1 here. Okay. So this was not deep. This was just notation, but a useful notation that you should get used to it, especially when working with Octave. All right. So nothing yet happened, just notation. So what is then what is here going to happen? Well, this is the key question, of course. So now the delta 2, so it was half just a while ago, just for example. The key thing is that's now something that we don't know. And how do we find out? What is the definition, or what is the implication of what the delta 2 here must be? All right. So this 7.13 here. Here on the right hand side we have the original influence of our rapid deployment force. So here we calculate the influence of the rapid deployment force when everything else is unchanged except that the influence of the Atreides conscripts is increased by delta 2. So this is what the C plus delta 2 E2 means, as we just saw. Okay. Now if this is bigger than this, then it is kind of also obvious that then this x2 star will be bigger than 0, otherwise this cannot happen. And yeah, let's hope that at some point it should happen, that at some point the Atreides conscript's influence is so big that it makes sense to use them. Alright, and now the question is at which point. So how much should delta 2 be? And now there are two ways of solving this, as also that we have learned in the case of shadow prices. So the lambdas, that if the change is small compared to the whole thing, then we can just read them there. A similar thing is true here. So a safe way of solving this would be to calculate first this, and then calculate many different LPs of this type, where this delta 2 starts from 0 and maybe increase a little bit, and try to find out where is the point for delta 2, so that this that begins with an equality if delta 2 is 0, obviously because they are the same. If I increase delta a little bit, maybe this doesn't change, a little bit more, maybe it changes a little bit more, now it changed. And maybe then I go a little bit step backward and try to find out the delta 2 as precisely as we want, maybe up to 1 or 2 decimal points, who knows. So at some point there is an inequality here, and this is kind of gives us an estimate of the delta 2. So this can be done. It's kind of hard work because there are many LPs to be solved. Luckily it's not hard work for us, it's hard work for the computer. And a computer, this is a small LP, it will solve these very many hundreds of them very fast. So is there any work for us? Well, of course there is. You have to program this. So this is the kind of forking technique that you probably, if you know your programming, you know how to do it. If not, then this is a good time to learn. Or you can just try it in a for loop, say, where delta 2 goes from, I don't know, 0 to 10 with the steps of 0.1. Maybe that will do it. Maybe that will give you an estimate. Okay. Then another thing, there is an unsafe but a more informative way of solving this problem 7.1, and that's basically just to check the reduced costs of the optimal solution Z star X star, where we are looking at this problem. And this is precisely what happens next, and this happens in the next video, and that should be the key example or key part where we explain via example what the reduced costs really mean. See you in the next video.